All right, so this is our last lesson in the force section, and we're going to talk about work, energy, and power. So those are our three pieces. They're interrelated, they connect really well. So this will summarize. It may be a slightly longer lesson than some, but you can pause, fast forward as you need in order to get through. I don't know if I showed you this little cartoon before, but I thought it was a great cartoon. Sometimes in math, this is how we feel, especially when we get talking about some of the physics principles. You go, where do we use them? I love this one. He's here, force equals mass times acceleration. It fits beautifully in with our Newton's laws. He's figuring out, well, what's the trajectory I have to throw it at? Got some trig in there because we found the other day that angles can come into play. We won't deal with that a whole lot, but we have a little bit. And just as he's starting to figure out the force that he needs to throw with, he's hit with a snowball. Physicists always lose snowball fights. I think it's a great little cartoon because I get it if that's how you feel, but the truth of the matter is you use that physics all the time. You just don't necessarily do all of the calculations while you're doing it. So if you think about it, if you're trying to hit somebody with a snowball, you may not sit and do the calculations like we have in class, but you do use all that thinking about force. You just don't use those words. It's kind of one of those things that we get so used to it, we kind of forget. Anyway, there's your little, hopefully, laugh for the day. So the first thing I want to talk about is the physics concept of work. In physics, work is the result of a force causing the displacement of an object in the same direction as the force applied. Now that can make a little bit of a funny concept for some people. So the two big things to take note of is the force and the direction. The force and the direction of motion have to be equal. So work equals force, or have to be in the same direction. Force times distance, and these must be the same direction. Now work, because it's force times distance, is measured in Newton meters, but we don't usually use the word Newton meters. We save that for when we're doing torque, and we use the word joule. A joule is what work is measured in. We're also going to find that joules is what energy is measured in. We'll talk about that when we get there. Our displacement, or the distance of movement, is always going to be in meters, and the force applied is always going to be in newtons. Now, the whole physics concept of work can be a little bit confusing. So what is work done in physics? Well, in physics, if you're pushing an object a distance or lifting it to a height. So here you're pushing an object a distance. This is work. Let's say you have a person and we take a box and we lift it up. That would be work. But especially if this was our original location. But here we have a server walking around with a tray, holding it at a constant height. The height of the tray is not moving. Okay, they're just holding it. Because the direction they're walking and the force that they're pushing up on the tray are not in the same direction. In physics, we would say that's not doing work. That's why the cartoon says this is great pay for not doing work. If you know somebody that's a server in your life, don't give them this one. They won't appreciate it, I'm sure. So in physics, if you're pushing against a wall and the wall does not move, you're not doing work. Or if you're holding an object at the same height, you're not doing work. Okay? I know your muscles get tired, so you know you're using energy, but we're just looking strictly at the physics definition of what is work. So is work being done? A briefcase is being held at a constant height while the individual walks around an office. Their arm is pulling upwards on the briefcase, but the direction that they're moving is perpendicular. It is not the same as the direction of the force. Therefore, they're not doing work. What about a lawnmower being pushed as shown in the diagram? Well, you can see their force pushes down on the handle and they're walking forward. Is work being done? Well, in this case, you might say, but the force is not in the same direction as the distance. What we need to stop and think about is it really not in the same direction? You'll see here this light triangle in the background. Remember we talked a little bit about triangles before? See, if you push at an angle, some of that force is forward and some of that force is downward. So what you would need to figure out is how much of the force is in the same direction as motion to find how much work you've done. So in this case, yes, some work is being done, but not all of the force is in the same direction. So we'd have to find out what portion of the force is horizontal or in the direction of motion. We're actually going to do that in our next example. So this one, how much work is done by an individual is done. I've got some words missing in here. I apologize. Sometimes you write things and you think all the words are there, and then you start reading them later and you go, what the heck? How much work is done by an individual pushing a lawnmower with an applied force of 115 newtons around their yard for a total distance of 1.5 kilometers? So you're kind of zigzagging back and forth a lot. Quite a lot if you do 1.5 kilometers. The mower handle is at an angle of 30 degrees from horizontal. So like I told you before, we're pushing down. So I'm going to draw the force triangle. So they're pushing down and this force is 115 newtons. That's on the handle. And some of that force would be forward, but some of it is straight down, pushing down to give you grip. Otherwise, you spin your tires or the lawnmower's not going to keep going. So we need to figure out how big is that force. Now we're told that this angle is 30 degrees. So it's quite easy to calculate. We go back to our trig from one of the very first units that you've done. If we look, this is our adjacent side, and this is our hypotenuse. The formula that uses adjacent and hypotenuse is cosine. Cosine of an angle is equal to adjacent over hypotenuse. Substituting in some values, cosine of 30 degrees, that's the angle of my push, is equal to the force that's in the same direction as I'm moving. So let's call it force parallel to the distance. I like those. Parallel helps us remember they're in the same direction. And underneath the hypotenuse is the force on the handle. How much force is the force parallel? Well, it's going to be equal to the cosine of 30 times 115, which gives us a force of 100 newtons. I was going to do a quick double check. I got caught a couple times the other day with copying the wrong numbers down. And we're good, 99.59, so that would round us to 100. So 100 newtons of force. So now we can find out work. Work is equal to the force parallel times the distance. So force parallel is 100 newtons times our distance of 1.5 kilometers. We need to change to meters, so that would be 1,500 meters, which gives us a grand total of 150,000 joules, or we could say 150 kilojoules. Oftentimes we'll use kilojoules. You'll see even if you're looking on the package or the wrapper of a food product, they'll often give you the energy consumption in kilojoules. So that would tell you how much you could eat to do that work. Okay. So quite easy. The trickiest part of this one is doing the trig to find out what part of the force is in the same direction as the motion. Let's look at a second question. In the absence of friction, it takes the same amount of work to lift an object to a certain height as it does to push it up a ramp. Now we're going to investigate this a little bit more when we get to simple machines, but for now that's a fact that will allow you to do some calculations. How much work is required to lift a 135 kg object 3 meters? So we're going to start with this picture. Okay, so this is 135 kilograms. And our distance is 3 meters. What is the force we have to apply upward? Well, the upwards force, we are working against gravity, so we need to find out what is the force of gravity, because that's the force that we're pulling upward to move this object. That's 135 times 9.81, which is the acceleration due to gravity, which gives us a Helps if I have my notes here, which gives us a total of 1,324 newtons. Work, so gravity is in the same direction as the distance, so the work done is going to be 1,324 times 3 meters, which gives us a grand total of 3,973 joules. That's the amount of work that we would have to do. For B, how much force would it take to push the object up a frictionless ramp that's 5 meters in length? Well, we just found that the work up the ramp is equal to the work to lift. Okay, so the work up the ramp is going to be the force up the ramp times the distance of the ramp is going to be equal to the work to lift, which was 3,973 joules. So we're going to find our force times, it's a 5 meter ramp, it's equal to 3,973 joules. Dividing that by 5, we find that the force to push the object up the ramp is equal to 795 newtons. So to lift this object, I would need around 1,300 newtons. To push it up the ramp, I need about half of that. So you'll notice pushing something up a ramp means I use less force, but what it also means is you have to push a longer distance. We're going to look at that a little bit with simple machines. That's how we can use that in the information in the question to solve the problem. C, how will the presence of friction impact the amount of work required in the two scenarios? Well, friction won't change the first scenario. I guess friction in the motor could. But I'm thinking when you're lifting, friction's not as big of a concern because you don't have two surfaces in contact unless there's a motor involved. But when you're pushing up a ramp, the longer the ramp, the more friction, so the more work you would have to do. So friction will increase the work. So friction, I'm going to say it this way, friction increases force, which increases work. Okay, so there's more force to work against. So I have to put in more work to get over it, which means there's more work overall. And one final question, how much work is required to lower the 79 kg dummy 3.65 meters at a constant velocity during a rescue simulation? So sometimes people will be simulating doing a rescue from a height. This is a common setup you would see if you walked into the wind turbine shop. And how much work is required? Well, if you want to lower them at a constant velocity, let's just think about the picture. If this is my person as a dot, if I want to lower them at a constant velocity, the force of gravity pulls down, so the force applied is the upward force, and they're equal to each other. Okay, so the force that I have to apply as I lower this person has to be equal to the force of gravity. We're not just letting gravity do the work. I'm working against gravity so that they're going down slowly. So the first thing we're going to do is we're going to find, well, what is the force of gravity? So 79 times 9.81 leaves us with 775 newtons. Now that we have that information, we can figure out the work done. I have to apply a force of 775 newtons over 3.65 meters, and both of those forces are in the vertical direction. They're in the same direction. So the amount of work that I've done is 2,828 joules of work. Okay. So you've done 2,828 2,828, get the numbers all straight, joules of work in order to make them slowly lower. If you let gravity take over, well, you would do less work, but the individual could potentially have substantial injury. So the next piece that we want to talk, so we just talked about work, so we're going to take a minute and talk about energy. Energy is defined as the ability to do work. So it's how much work can be done. Energy is required to do work. It's what's used to do work. And as a result, both work and energy are measured in joules. So when we talk about work, we could easily just replace the word work with energy. In a mechanical system, the work done on a system is equal to the change in kinetic energy. We'll talk about what exactly kinetic energy is. The other thing we need to know about energy is the law of conservation of energy. It says that energy can neither be created or destroyed. There is a set amount of energy in the world, and that energy is neither being made or taken away. It's staying constant. Energy can neither be created or destroyed, and the sum of all energies in a system is constant. So when we look at our problems, we're going to look at them as isolated systems where energy is neither created or destroyed. We do know that sometimes energy gets transferred, and we'll talk about that. So there's two types of energy that we're going to talk about. The first type of energy is potential energy. It's stored energy that can do work. It's like I often describe it as students that come into the class in September. They're full of potential. They have the ability to do work. The question is, will they choose to do work? In physics, potential energy comes from the change in height of an object. So you will see this individual on a bicycle, they have to put in energy to get up to the top of the hill. At the top of the hill, there's potential energy due to the height they are above the hill and the effect of gravity. So gravity can do work on them. The amount of force due to gravity is equal to the weight of the individual on their bike times 9.81, or just technically I should just use the word weight. You don't have to think about the other because weight automatically assumes you've multiplied their mass by 9.81. So the weight of the individual times the height above the surface that they are, or the height difference from when they started and where they ended would be their potential energy. Gravity isn't doing work when they're at the top, but it has the potential to pull them back down. And that's when the individual doesn't have to do work. They're going to get out of the bike the work they put into it to get up to the top. So kinetic energy, on the other hand, is active energy. It's doing work. It's actually engaged. And in physics, this is the energy that causes the motion to occur. Now, when we think about the forms of energy, I like this chart because it categorizes them quite nicely. So potential energy is stored energy, and there's lots of types of stored energy. Chemical energy, that's batteries, food, all kinds of things there. Elastic energy, if something's stretched or you have a board and it's kind of sprung a little bit and can go back up, that's a type of potential energy. It's potential energy before it springs. Once it springs, it goes to kinetic because it's moving. Nuclear energy and gravitational energy. So gravitational energy is really, this is the one that we would be involved or considering. Now for types of kinetic energy is due to movement. Heat causes movement, so it's kinetic energy. Mechanical energy, that's the one we're actually going to look at, is when objects are in motion. Electrical energy, particles moving through a wire. You've already talked about current. And magnetic energy causes a push or pull. Magnetic energy, I would argue, could go on both sides here. I think you could argue that one a little bit. And then there's other types of energy. We've got sound energy and light energy that kind of are off on the road. Now I want you to stop and think for a second. We're going to apply the law of conservation of energy, that energy can neither be created or destroyed, to answer this question. If energy is neither created or destroyed, why is energy system and energy transfer in a motor never 100%? So the energy that's drawn to power this fan is not completely converted into kinetic motion. Where is the motion? Well, where is the energy gone? Well, the energy is just transformed. The energy is transformed into often non-useful forms. Okay, so that's where the energy goes. So what is it? What does it end up being? Well, we have heat, which is caused by friction. I can tell you for a fact, my computer is not 100% efficient. If you put your hand anywhere as close to the bottom of it right now, it would be quite warm, especially after I do a Zoom lesson. So heat causes energy to be lost, and it's typically due to friction. It can also be due to electrical components. So that's one of the biggest places where energy can be lost. Now for you in your trade, when you're dealing with heating, there might be times when you can harness that heat and it can still be considered useful. But in the case of the fan, if you put your hand on the housing, you feel the warmth, that's where the extra energy is being lost. In the case of a fan, we also have sound. So some of the energy is lost in sound. Hopefully we don't have light. If we have light, something's arcing somewheres. But those are some of the examples of where we can lose energy. And it's not that it's lost, it's just that it's being transformed into a non-useful form, and we're not concerned about getting work out of it. It's energy we can't get work out of. It's doing work on things that we don't want to do work on, basically. So just a little bit more depth on the two types of energy. So gravitational potential energy, I told you that was the one we were going to talk about the most. And the formula for it is potential energy, EP, is equal to mass times gravity times height. So mass is going to be kgs. G is the gravitational constant or acceleration due to gravity that we dealt with before. And h is always going to be the height above the Earth. We'll just talk about a couple examples of gravitational potential energy. Kinetic energy is energy with motion. You'll notice when we deal with kinetic energy, we have speed or velocity. Okay, so with kinetic energy, we have 1/2, it's related to the mass. The heavier the object, the more energy it takes to move, which makes sense. The faster the object is moving, the more energy it takes. That makes sense. So either one of these it increases the amount of energy required or the amount of energy used. So that's what it's related to. A mass is still in kilograms and our velocity is meters per second, like we've had for some of our other questions. So I want you to do another kind of think and apply question. I want you to compare the energy that would be required at startup, at low velocity, and at high velocity. So just a qualitative comparison. What's happening at startup? When this fan turns on, we have acceleration until we get to a constant velocity. If there's acceleration happening, we'll call this A, B, and C. If at A, if there's acceleration, there is more force. So more energy would be required. Okay? And you can often hear that. You notice you'll put out, I know our ceiling fan, you pop the ceiling fan on and you can hear the motor laboring. That's requiring more force, there's more load. Now, if you were able to track the amperage on the fan, you would see a peak at the beginning. And the amperage is related to, the amperage is like a way of measuring how much load there is. If it pulls more current, you'll see a little peak, and when it pulls more current, it's trying to get more energy in order to be able to turn over. So at the startup, there's acceleration. Acceleration means there's more force, so more energy is needed. Then once it hits a constant velocity. Okay, so you're going to see a slight increase. B, what about at low velocity? At low velocity requires less energy. See high velocity, more energy. So let's just think for a second. So let's just imagine I've installed a new heat pump. Well, let's not even say it's a new heat pump. Let's say I've had a heat pump for a couple years. Let's say this is maybe actually a real life question. And when first using the heat pumps, they were usually ran on an auto setting. Now that heat pump is installed above a window. So the cool air off the window, and there's a fair bit of cool air off the window, means the auto setting for speed control and temperature control doesn't work properly. So the fan is constantly running at high speed. Okay, so that's our first scenario. Power bill is found to be relatively high, much higher than was expected when using the same heat pump in a different house, in a comparable area. One of the questions was asked was, why? How come this heat pump's not as efficient? It's the same unit. What's going on? Well, what we discovered, now this is not as hypothetical as you can probably tell. This is something that we discovered when we moved into our latest house. We've been in it for 2 years, the end of this month. The first thing we did was we installed some heat pumps, and our favorite brand is the Mitsubishi Mr. Slim. We've got 3 of them. We had 2 of them at our old house. It's our favorite brand to work with. I think it's partially because we had really good service from the company that installed them. That goes a long way. So remember that as you're out working with people. But we found the heat pump just didn't seem to be as efficient as the previous ones we had. And I said to my husband, especially when we got into the next winter, I said, I think I know what's going on, because after a year in the house, you kind of got used to things that were in it. And even though we'd had heat pumps for quite some time, we kind of forgot that if you put it on the auto setting and the heat pump is above a window, I'm hoping to have it moved, but it's above a window, the cool air off the window makes the heat pump think the house is cooler than it really is, so it bumps up the fan speed to put out more heat, okay, to transfer more of that heat into the room. Higher fan speed means more energy is being used. We found that we could run the heat pump just as much, but we dropped the fan speed to low. And when we dropped the fan speed to low, we noticed a remarkable difference in our electricity consumption, and we were using less energy. That's one of those really simple E equals 1/2 mv squared. Decreasing the speed of the fan decreases energy consumption. One of those things you really don't think about, how much energy is consumed just by the fan that's required to push out heat. So one of those things that think and apply, that's one of those think and apply scenarios that came up in a very real life context that actually relates to you. So I would argue, you can tell me otherwise if you want, I would argue don't run your heat pump at a fan speed any higher than is needed for comfort, simply because you're wasting energy if that's what's happening. Now you can tell me if you think that's true or false. I'm just simply applying physics and watching my energy consumption on my power bill. One more question. I think this is, maybe I have 2 questions. I do, I have 2 questions, but these are really quick ones. So this is just a couple calculation questions. A 75 kilogram individual has a 1.8 meter harness tether. So you're working up on a roof, and that's your harness tether. What's the difference in gravitational potential energy when they fall the length of the tether? So we want to think, okay, here's the individual up on the roof. My great art skills, I'm not even doing good with stick people. So they're up on the roof and they fall down 1.8 meters. And now they're dangling here. What is the change in energy? So how much from the energy they had before the energy they have when they're down 1.8 meters. Well, the change in potential energy is just equal to the change in their height. So we use the potential energy formula. So potential energy is equal to mgh. So the mass of the person, which is 75, times the effect of gravity, times the height difference that they fell, which was 1.8 meters. The difference in moving a difference in height is going to be directly proportional. It's going to give us the change in energy. Multiplying those together, we would find that the change in potential energy is 1,324 joules. Okay, so that's their change in potential energy. They lost 1,324 joules. Now that energy wasn't lost. Instead, it's converted to kinetic energy, which is B, because they're moving. They have a velocity here. So up here, they have potential energy, and down here, they have kinetic energy. So we're transferring that potential energy, this amount of potential energy, into kinetic energy. Well, let's figure out how B says what's the speed they'll be moving when they reach the maximum length of the tether. So we know how much potential energy they've lost. That's been switched to kinetic energy, the energy that's fueling their motion. So we can just do a simple substitution. 1,324 joules is equal to half times 75 kg times velocity squared. So we get 1,324 equals 37.5 v squared. Simple rearranging. Velocity is equal to, v squared is equal to 35.3, and then take our square root. And velocity is equal to 5.9 meters per second. So they're falling at a pretty good clip. So that would be their velocity at the end of the tether. That's why when you fall, when you hit the end of the tether, you feel that really good snap. It's because you're going from a velocity of 5.9 meters per second to 0 in a short amount of time. So that's what gives you that substantial force. Last question, nice easy question. How much extra energy will you expend or spend if you're carrying 15 kilograms in tools and climb to a height of 4.5 meters? So you're lifting yourself, but how much extra energy is required to lift the tools? Well, 15 kgs times you're working against gravity, so that's 9.81, times the height difference of 4.5 and meters, and you would find you will burn an extra 662 joules of energy. So the question is, why are you tired when you lug more stuff around? Well, it takes more energy to move it because you're fighting gravity a little stronger. So the last thing I just wanted to do is summarize. This slide doesn't say a whole lot, but summarizes it well. We started out with speed, and we knew speed was what controls acceleration. Oh, I've got an itchy nose, I'm sorry. Keep rubbing my nose. So speed is what we started with. Speed was the change in the distance something's moved divided by time. That was speed or velocity. So speed, a change in speed, is what we call acceleration. If there's acceleration on an object, the object has a force acting on it. If there's a force on the object, typically there's work being done, especially if it's moving a distance. If work is being done, it's requiring energy. And if energy is being put in, that's what's causing speed. So it's a full cycle. And that's why we kind of put all of those pieces in together, is trying to get you to think about how all of that all interrelates. So thinking of fan speeds, I know we haven't really talked about circular motion because that gets us, we don't have enough time. We'd have to like a full year of physics in order to really talk about all the pieces that you deal with. But in terms of speed, as a fan speeds up, there's acceleration. That acceleration means there's a force from the motor being applied. That means the motor's doing work, which means there's energy. So it's a very full cycle that connects really, really nicely for all of the pieces. So there's a short quiz for you to do just to summarize that. And if you have any questions, please don't hesitate to let me know.